Okay, today's lecture is going to be about shocks and failures, specifically with regard to electric power systems and markets. So shocks and failures are, sometimes those words are used interchangeably to describe, extreme unexpected events. But they're actually different. A shock is an event that produces a significant change within a market or a system, but is ultimately caused by some sort of external or exogenous force. They're unpredictable, and they typically impact supply or demand throughout the market. And we'll go through some specific examples for electric power systems. A failure is when a component of the system internally breaks down and can't function normally. And typically in electric power systems, the failure is affecting the supply side of things, the availability of generation, whether that's conventional, thermal generation, coal, nuclear, natural gas, or renewables. Now, in both cases, they're hard to predict, right? And that doesn't mean they're unexpected. Given a long enough sort of horizon or planning horizon or simulation period, we do expect to see shocks and failures, and so we have to incorporate the likelihood that we encounter these extreme events when we're not only designing systems in terms of making choices about infrastructure, but also in how we operate systems dynamically. So to some extent, these are normal events, right? We want them to be as rare as possible, but we always assume that there's a chance they can occur. So let's talk about shocks first. If we're thinking about power systems and markets, and those are inextricably linked. The operations of power systems on the physical side inform and constrain the way that the market works and how prices are determined. We're talking about two different impacts on supply and demand, and so this figure shows the conventional way we think about the interaction of demand curves and supply curves. And if you haven't had microecon, this is going to seem a little strange, but if you have, this should look really familiar. So market prices for any sort of good, and in this case we're talking about electricity, are set by the intersection of the demand curve and the supply curve. And the shape of the demand and supply curves are driven by preference, really. So we all have a preference about at what price we would be willing to pay for something, and then on the supply side, suppliers have prices at which they're able to supply a certain amount of goods in order to recoup their operational costs. So where these curves intersect along the y-axis corresponds to the market clearing price, so the dollar per unit value that all providers of the goods would receive, as long as they're below this point on the supply curve, or to the left of this point on the supply curve on the x-axis. So specifically for the power sector, we can develop supply curves using a pretty explicit representation of the variable costs of different generation technologies. So on the y-axis here you have the marginal cost, the marginal system cost. So the additional dollar per megawatt hour that you have to pay in order to get one more unit of electricity at each point along this x-axis, the cumulative supply of electricity. And so in this case, we have an entire system's worth of generation along the x-axis. So the furthest point out on the x-axis is the total amount of electricity our system could supply if it were stretched to that point. And on the y-axis, we have the corresponding variable or marginal cost for each one of these generation technologies. And so that we're in some sense stacking generation. So we're cumulatively adding total, quantity of electricity that we can supply in order of increasing cost. So we start all the way on the left with hydro because there's no fuel cost associated with hydropower production. And so for all intents and purposes, we're assuming that the marginal cost is zero. Nuclear, really efficient base load generation has also a low marginal cost. Then we get into coal, natural gas, and then the generators of last resort are really oil combustion turbines. So very expensive, but we tend to include them in the system mostly as a backup or a unit of last resort. So this discrete representation of the system supply curve can more or less be translated into what we would normally think of as a shape of a system supply curve. And for demand, we have very little price elasticity of demand, right? So what that means is that when we are making decisions about when we use electricity as consumers, price really doesn't factor into it. At least any sort of sense of a dynamic price. We may vaguely have this sort of desire to save electricity or to save, reduce consumption in order to reduce costs, to reduce our electricity bills. But we are not in any way making incorporating any understanding of the dynamic nature of electricity prices and realizing, if the price goes up, how much, am I willing to buy? How much less am I going to be consuming in response to that change in price? So in other words, demand is sort of a constraint on the system here. Consumers have electricity demand, and that collective electricity demand gets sent to a market or a system operator as a constraint that has to be met. So there's no real choice in whether we get, if we meet 99% of demand or want to provide slightly more than what's demanded. We just have to provide the exact amount of electricity production that meets demand at any given point. So that's why the demand here is a vertical curve. And so the intersection of that vertical line with the system supply curve that we directly model from this discrete representation of the individual power plants in our system, the intersection of these two then give you a market clearing price. So the point on the y-axis where these two curves intersect is the market clearing price. So let's look at a specific example of a market shock that would impact things on the demand side. So I talked about demand being a constraint on the system, right? The shape of this demand curve is vertical. So things that can push it to the left or to the right. And usually we're more concerned with situations that could unexpectedly push demand significantly to the right. An example of that we've experienced fairly recently is the peak in electricity demand, that occurred as a result of the polar vortex in the winter of 2014. So this figure shows on the y-axis megawatts, and I guess you could consider that megawatt hours. And on the x-axis, different markets or ISOs in the United States. So you have the Midwest Independent System Operator, MISO, the Southern Plains, PJM, which we've dealt with a bit before. That's most of the East Coast, or the Mid-Atlantic up to New York. And then New York, which is specifically for New York, and then ISO New England, ISO-NE. This shows the previous winter peak and then the winter peak for the polar vortex in red. And so you can see that that's not a huge jump in any case, at least relative to previous winter peaks, except for MISO, and that was pretty significant. But a very small shift to the right in terms of demand peak demand can have a pretty big impact on price, and we'll take a look at why. So if we're thinking about demand shocks, either heat waves or cold snaps like the polar vortex, you're talking about an increase in peak electricity demand usually. And so in this case, if we're talking about the polar vortex, we're maybe moving from this solid red vertical line to the dotted red vertical line. So we're going from a situation in which we're already talking about peak demand, the period of the day in which electricity demand is highest. And we're moving that even higher because of extreme weather. And so you can see that because of where we are on the supply curve, we're already pretty far to the right. We're getting into this zone where incremental changes in electricity demand that go to the right result in nonlinear increases along the supply curve, right? So as we go further and further to the right, a rightward movement on the x-axis results in a greater movement on the y-axis, right? And that's the danger. I mean, I think that's why power systems are susceptible to shocks. Because of the shape of this system supply curve, it looks exponential as you get out towards more extreme demand periods. So we can also think about shocks in terms of impacting the availability of generation. And we've talked a little bit about that through our discussions of weather and climate and variable renewable energy, etc. This is a nice visual example of how supply shocks can occur and impact variable renewable energy production, and how that can have a big impact on markets. So there are these three figures of North America, and they go from left to right, the first, second, and third quarter. So first quarter is January through March, second quarter is April through June, and the third quarter is July through September. And the colors represent the percent departure in the average wind speed for that quarter relative to the period 1988 to 2014 for the same calendar quarter. So blue and purple would represent really significant, dark blue and purple would represent really significant negative anomalies, right? So well below average wind speeds, whereas yellow and orange would represent positive anomalies, so increased wind production relative to the historical record. And here's another way of looking at that same data that's specific to West Texas. And there's a lot of wind capacity built into Texas, and it's been in some cases very beneficial in terms of weaning that system off of fossil fuels, and they've built out a lot of transmission and have done a great job in some cases of reducing some of the negative aspects of having that much wind in the system. Now, one of the challenges of wind that you really can't address, or it's very difficult to address, besides just building extra redundancy into the systems, is the possibility that you have periods where you just have really below average wind power production. And so you can see that we have a signal in black here that's annual or quarterly wind speed anomalies. So if you're at 0%, you're at average. And then you have also a smooth or some sort of filtered signal here in blue. It looks like maybe it's, I can't tell just looking at it, how many months they're filtering at a time. But you see some periodicity, right? We have periods of high and low wind power production. And then you can see most recently in 2015, this area of Texas experienced an incredibly large negative anomaly, right? And so the other way to look at this, if we're thinking about things probabilistically, is to sort of turn this figure on its side and think about 0 as being the mean and the deviation from 0 being the standard deviation, right, or the variance of whatever distribution this is. We have a mean-centered process, and we're looking at, a process that has considerable variance, right? It can get up to above 15%, and in the case of 2015, below 15%. So you can think about where in this distribution 2015 would land, and it would be at the very, very lower tail, right? This would be a very rare, sort of very low probability event, but it's one that you have to sort of plan for. And so when the state of Texas is, or not the state, but the system operator of the state of Texas is thinking about how to value wind capacity, right? So if we're building more and more wind capacity into the system, does that mean we can retire coal plants? Does that mean we can retire natural gas plants? And it all depends on, how far away from 0 it's possible to drop here, right? So if wind only dropped to 5% in the worst case scenario, you could replace more coal and natural gas with wind than you could if it's possible to experience years in which wind deviates from 0 down to negative 15%. So we may have looked a little bit at this before. If you're losing renewable energy, and that could mean being in the middle of a drought and you're losing a lot of hydropower production, or if you're in a wind drought, or if you experience a solar eclipse, that has a direct impact on not demand, but the system supply curve. And in particular, what it does is it shifts the whole thing to the left, because you're reducing the amount of generation all the way to the left that has a really low marginal cost. All these renewable energies have no fuel cost, so we generally assume that their variable cost is 0. So if you take those out of the system supply curve, the whole thing moves to the left. And what you can see the result of that is that the intersection between the vertical demand curve, now we're assuming demand is not changing just because you're in a drought or a water drought or hydrological drought or a wind drought. The demand's not changing, but the system supply curve does, and as a result, the intersection of the vertical demand curve and the system supply curve occurs at a much higher point along the y-axis, and so the prices increase. Another thing that we definitely have talked about is the impact of extreme weather on the supply of natural gas. We talked about that in the context of commodity markets, but also the impact of weather and climate on energy systems. And a really, really famous example, of course, is Hurricane Katrina, which directly hit New Orleans and disrupted a lot of refinery activity in the Gulf Coast, which is sort of a hub for oil and gas production in the United States. So if we're thinking about the impacts of a Gulf occurring hurricane on natural gas refinery activity, which can dramatically decrease the availability of natural gas throughout the United States, that would increase prices for natural gas, right? And if we have increased prices for natural gas, and we sort of talked about how that can directly be passed through to the cost of electricity from natural gas plants. So fuel prices, remember, the amount of money, or the fuel costs, the amount of money that a generator has to pay for fuel costs is directly related to its heat rate, so the efficiency of the power plant, but also, and how much electricity it's producing as well, but also what the price per million BTUs of fuel is, and that we could talk about natural gas in this case, or coal, or oil. And so if the price of natural gas goes up, that directly impacts the shape of the system supply curve. So the part of the system supply curve that is associated with natural gas plants changes, right? And the marginal cost of electricity production from gas prices, from gas plants, all increases. And as a result, the new system supply curve intersects with the demand curve at a higher point along the y-axis, and so wholesale electricity prices increase. Okay, so that's system shocks, and now let's talk about system failures. Remember, system shocks are extreme circumstances that are sort of forced upon the operations of a power system, whether it's extreme weather or changes in commodity prices, or a lack of availability of variable renewable energy. System failures are a little different. Within the context of electric power systems, we're talking about the failure of specific components, and so there are three main classes of, I would say, of infrastructure and electric power systems that we would sort of talk about. And it's a little more complicated than this, but we generally lump things into generation, transmission, and retail distribution. Transmission being high voltage transmission, distribution being much lower voltage transmission lines that take electricity after being transformed off of high voltage transmission lines and deliver them to end use customers. So at any point along this interconnected infrastructure system, we can experience failures. Sometimes those failures are forced, and that means that a power station or a generator or a transmission line or distribution line is unavailable to produce power or transmit power for unexpected reasons. In other words, we didn't see this coming, and this can be caused by equipment failures, disruption in supply chain, operator error, weather, climate, and other sorts of random events. An unforced outage is a little different. That's something that we plan on, right? That's sort of like routine maintenance or taking things out of operation in order to make improvements. And that can happen for transmission or generation. That's a little different than a failure, right? That's something that we have to incorporate when we're thinking about system operations and plan ahead about when we're going to take things offline in order to do maintenance or improve them. But that's a little different than when we're talking about a system failure. When we're talking about a system failure in power systems, we're really talking about forced outages. We quantify, the main regulatory body that oversees the reliability of power systems and tracks that reliability using a variety of metrics is the North American Electric Reliability Corporation, or NERC. And they have a variety of metrics for measuring the reliability of power systems and power plants in particular. And so one measure that they use to quantify the reliability of power plants is the equivalent forced outage rate, or E4. And the equation for that is listed here. So the way you calculate this is, on the numerator you have the sum of all hours during the year in which the unit is forced offline, FOH, plus the sum of all hours during the year in which the unit is forced to derate or partially reduce output. And you translate the EFDH to an equivalent number of hours, full offline hours, FOH hours. And in the denominator, then you have FOH hours plus the EFDH hours plus the SH, which is the sum of all hours during the year in which the unit is online, and synchronous hours, which is the sum of all hours during the year in which the unit is online but not producing electricity. So it's spinning at the right frequency. Remember, power systems are alternating current systems, so they all have to operate at the right frequency in order to actually deliver electricity or provide some sort of backup or reserve potential. And so if the power plant is spinning at the right frequency, even if it's not producing electricity, we're still assuming that it's online and operational and could be called upon to be useful if needed. And then pumping hours applies to all pump, storage, hydro. And then we multiply this fraction times 100%. So the whole idea here is to get some sort of percentage number of hours per year in which the power plant is not reliable, not online and able to be used. These are hours in which the plant is experiencing what we would think of at this point as forced outages. So outages that they were not expecting to experience. So NERC keeps track of statistics for all power plants, and I think some of these statistics are based on numbers that are volunteered, or I think NERC sends out surveys to generators, and then it's up to generators to list that information for each generator. Now, you could imagine that this would be somewhat proprietary information. If you're Duke Energy, you don't necessarily want your competitors to know how reliable all your power plants are, because that might give them a better idea of when Duke Energy would have to go onto the wholesale market and buy replacement power if one of their system components went down. And that would be sort of a competitive advantage for whoever the seller of that replacement electricity would be. So what NERC does is they get all this information and they make it anonymous, and they group all the statistics by category. So this table here shows for all fossil power plants, so that would include natural gas, coal, and even oil. And they group it by size, and size here meaning generation capacity, down from 1 to greater than 1,000 megawatts. And then you can see the number of different units that were reporting. We have a total of 985 fossil units that were reported. And then we see the equivalent forced outage rate listed all the way to the right for each size class. And so across all sizes, it looks like about 10%, 10% failure rate. And so what that means is that, for example, in the last category, for the really big fossil fuel power plants greater than 1,000 megawatts, we have 7 of those units reported. On average, each of them experiences a 12%, 13% failure rate among all hours in which the plant is not deliberately offline, right? So that means that for every 100 hours that the plant wants to be on, about 12% of those, the plant is forced offline, and this isn't related to volunteered or deliberately bringing units offline for maintenance. And so that's a pretty high number, right? If you think about what else in our lives do we really think about as having a 12% failure rate? You certainly don't think about that about your own electrical devices that you use, like 1/8 of the time, 1 out of every 8 times, whatever you're using breaks or doesn't work the way you want it to. That's pretty high. And so I think the reality is these are gigantic, complex power plants that are susceptible in a lot of ways to failures in different categories. And so that should inform you about the need for system redundancy and reserves in power system operations and planning. So this is partly why we have power systems where you have peak electricity demand, for example, in like the western part of North Carolina in the Duke Energy system, that's around like 18,000 megawatts, but the size of the system itself is 23 or 24, right? So quite a bit of extra capacity built in, and it's because power plants fail and other system components fail on a regular basis, and you have to have that redundancy built in order to ensure reliability. So there's a whole sort of field and a range of subfields that deal with modeling failure rates and system reliability. And one of the common ways of thinking about modeling failure rates and system reliability is using what are called reliability functions. And these are functions that describe the probability that a system or system component will maintain its functionality past a certain time. And so we start with a probability density function, which is shown in the bottom left. And on the y-axis we have probability or density, and on the x-axis certain values of t, which is time. And so the probability here is specifically describing the time, the probability of experiencing a certain time to the first failure. And so if we were curious about trying to figure out what the probability is, for example, that the time to the first failure will be less than or equal to some time we specify A, then we would, for example, in this lower left figure, take all the area under the curve that's to the left of A. And if we wanted to figure out what the probability is that the time to the first failure will be greater than A, then we take all the area under the curve to the right of this value A. And so mathematically what that's doing is taking the integral of this probability density function from t to infinity. For example, if we wanted to, in this equation at the top, figure out what the probability is that our time to the first failure is greater than some value little t, then what we're doing is taking the integral under this curve from t to infinity, right? So we're taking the figuring out what the area under the curve is to the right of the little value t. And that's equivalent to saying 1 minus big F of t, where F of t is the cumulative probability distribution associated with the PDF. And so each of these, a different underlying probability density function. The one we saw just a minute ago was this sort of normal Gaussian-looking distribution. But if the shape of that underlying density function changes, then the corresponding reliability function changes. So the reliability function here we're measuring directly as 1 minus the cumulative distribution function. And so what you can see is on the y-axis you have the probability that the system component will be operational past the value t on the x-axis. So if we go all the way to the left on the x-axis and we're at time 0, we have 100% reliability, which means that the probability of this system component lasting at least 0 time periods is 1 or 100%, right? And as you go out further into time, the probability goes down, right? So the reliability or the probability that the system's still going to be working past a certain time point starts to decline. But for these 3 different distributions, or 3 different systems here, you have much different looking reliability functions. Where the one in black, the reliability degrades really quickly, but then if you reach a certain time, then the reliability holds pretty constant, right? So if you really make it past time period 30,000 or so, 60,000, then the reliability is sort of constant. It's low throughout time, but it's fairly constant. For the blue one, you see a much more gradual, steady decrease in reliability as a function of time, almost linear. And then the green one, you see that there's very high reliability up to a certain point, maybe about 60,000, and then you experience this precipitous drop in reliability. So a related concept that you can, that's a more simplistic way of looking at it, is mean time between failures. So you can think about that underlying PDF function that describes the probability of a system component being reliable past a certain point, having a mean, right? A mean of that distribution, and that's really sort of analogous to what mean time between failures is. So this is the expected time elapsed between inherent failures of a system during operation. And so this can be calculated as the arithmetic mean, or you can think of it as the expected value based on this underlying probability distribution that forms the basis of the reliability function. You can also derive the mean time between failures empirically, right? So you can just say you might have a time series of on and off, right? For a power plant, you might have a record of how long it's operational before it experiences a forced outage, and then how long it's offline when it does experience a forced outage. And so this gives you a sort of binary signal, an up or down signal, and you can calculate the number of periods in between an up or a down, right? So assuming that you have to be able to tease out whether or not a power plant is shutting off because it's being forced offline or because it's just responding to some change in demand or market price or something else like that. But you can empirically pull out the mean time between failures for different power plants, and that's one way of modeling power plant failures. And I have this note at the bottom: do you think there's a seasonal component to mean time between failures? So one way of sort of looking at that is realizing that you're probably going to be using a power plant more during high demand periods. And so if you think of mean time between failures as sort of a constant parameter of operating a power plant, so it doesn't matter what time of year it's operating, but as every 1,000 hours the power plant tends to fail, then and you're using the power plant more in the summertime, and you're more rapidly or more often getting up to 1,000 hours or something like that of continuous time, then it sort of comes logically that power plants tend to fail more when they're being used more, and that tends to happen in high demand periods. Now, there are other reasons why power plants and systems can fail during high demand periods, and a lot of that has to do with the impacts of just higher environmental temperatures on system components, including transmission and distribution lines. But just from a purely arithmetic standpoint, if we're thinking about mean time between failures as remaining constant, then it just sort of happens that systems tend to be a little less reliable during high demand periods. So when we're talking about power systems, and we've gone through system shocks, we've gone through system failures. Shocks being impacts to power systems that are occurring because of exogenous variables, and failures being impacts to power systems that occur as a result of the failure of internal components. And we've talked a little bit about how we would describe, certainly from a system shock standpoint, whether we're talking about weather or climate or natural gas prices, we have some ability to make probabilistic guesses, right? We can fit probability distributions to gas prices, to weather and climate events, and figure out how likely they are to occur. Same thing with failures, I would say. Now, one thing that we've talked about recently, when we're talking about Monte Carlo simulation, if you wanted to model multiple different system components and try to figure out how often these system components were experiencing shocks or failures at the same time, one really important part of doing that is accounting for any covariance between these processes. That's one I demonstrated in class the other day when we were talking about joint probability distributions. If you're sampling two different variables that independently would have separate probability distributions, but there is this historical connection, this linear dependence between the two variables. In other words, you're more likely to have a shock or failure in a system component at the same time that you have natural gas prices, or at the same time that you lose hydropower production. Then that has to be part of the modeling process that goes into simulating system shocks and failures and trying to describe the likelihood that you experience a number of shocks and failures at the same time. So there are lots of fun historical examples of more than one system shock and failure happening at the same time. A really good example is the California electricity crisis. So in this case, I'm indicating some either statistical or institutional connection or dependency by these arrows, right? So the ones that are connected by arrows, like, for example, a hot summer and a drought in the Pacific Northwest, which was the sort of like weather and climate context for the California electricity crisis, directly put pressure on natural gas prices, right? So those things are somewhat related, as well as growing electricity demand and not enough capacity. That was sort of an institutional failure that again put high pressure on high natural gas prices. That also led the way for some degree of market deregulation in California's wholesale electricity market. And that opened the door for direct manipulation by different market participants, including Enron, who was a disruptive force on the wholesale electricity side, but also they directly manipulated natural gas prices as well. And so you had all these sort of things working together to create this sort of perfect storm. And I think our ability to model some of these events and processes can be kind of limited. I mean, we can understand the probability of gas prices going high, sort of divorced from all this other stuff. We can just look at the time series and figure out, fit a probability distribution to it, and then try to figure out how likely it is that at some point in the future we're going to have prices beyond a certain, point X. Same thing with weather and climate. It's really hard to fit a probability distribution, though, to changes in policy and the actions of individual actors, for in this example, Enron. Here's another example that's a little bit less driven by institutional failures and more by sort of coordinated, or correlated failures and shocks. The polar vortex of 2014, the main shock was this really, really severe cold weather snap. And that simultaneously increases electricity demand and increases and creates outage problems at coal-fired power plants. Both of those increased demand for natural gas prices. And then you had some institutional problems as well, in the way that natural gas prices and markets were functioning. And so high natural gas prices here then sort of fed back into wholesale electricity markets. We had this dramatic spike in electricity prices. So for power systems in particular, one measure of reliability. So we've talked about how to think about reliability for individual system components in power systems, or you can talk about the mean time to failure, or using reliability functions for power plants. But the specific metric that system operators use to measure the reliability of power systems, one of the main ones, is called loss of load probability. And so this is a measure. You're performing some sort of analysis to figure out how many days per year, on average, over thousands of years, simulation years, do you experience a system outage or a blackout, right? And so this directly informs a company like Duke Energy in the area of how much capacity they need to install in order to meet, and what type of capacity they need to install to meet some sort of desired reliability target, right? So if you wanted to make sure that at least your system was providing electricity 99% of the time, or 99.5% of the time, or maybe you express it as the number of days per year on average that you experience reliability issues. That can all be quantified for any sort of like experimental system and simulated over thousands of years to figure out, what combination of resources helps meet that target. And so the process of figuring this out involves combining electricity demand profiles, whether that's a time series of electricity demand, or specific, a combination of dynamics in an hourly electricity demand, but also what a prediction about what the peak electricity demand could be. Same goes with variable renewable energy production, especially as we get systems that are integrating more and more variable renewable energy into their systems. Schedules of generator outages, and so that would be unforced outages, right? So like we have to include in this analysis some time that we're going to deliberately take certain power plants and system components offline in order to improve them, and then also the probability of forced outages. And then the goal here is to determine the expected number of days during the year in which a shortage might occur, where we don't have enough electricity to meet the demand. So this is sort of a visual interpretation of what I just suggested. So we have some sort of generation portfolio, right? And that could be the existing portfolio for Duke Energy, and they may be thinking about what they need to add to that in order to meet electricity demand 5 or 10 years from now. And so they would come up with this specific portfolio, and we'll talk about how you represent that mathematically in a few lectures from now. And then you have load profiles, and we should have some idea now of how you would model electricity demand, right? You'd have to have some idea of what the peak electricity demand is going to be on a year-to-year basis, but then you could also use time series modeling to come up with hourly load profiles, scheduled generation outages, and then the probability of forced outages. And there are a number of ways you can model that, whether it's and we'll talk a little bit about that in the exercise in class. And then out of this generation portfolio, you have some idea of how much it costs to produce electricity, but also what the reliability is going to be. And in many cases, there's a direct trade-off here, right? Because cost tends to increase with increased reliability. And so you want to minimize costs and get the highest reliability possible. And so utilities have to sort of balance how reliable they want their system to be. You don't necessarily want to go to 100%. You might want to just go to 99.9. And getting that incremental improvement in reliability can mean a nonlinear increase in costs. And so that's something they have to be aware of. So they go through this process and they simulate the behavior of the generation portfolio under a lot of different circumstances. And if the output is some sort of loss of load probability or reliability that's less than the standard they set, then they have to go back and make changes to what their simulated portfolio is. And they could add different types of resources, add more capacity, add more flexible capacity, stuff like that, in order to eventually get to the point where, at least from the standpoint of a computational model, the system is reliable enough. So the last thing I wanted to kind of bring up is this idea of black swan events. And this is a theory that's been put forward by sort of a popular writer, Nassim Nicholas Taleb. He wrote a book called Black Swan. And this is just a term that's sort of used to describe some sort of event that's surprising, it has a significant effect, and these are events that we tend to inappropriately rationalize after the fact, right? I think the point here is to really suggest that there are certain events that we are not going to be able to predict, right? That are really resistant to any sort of probabilistic understanding, which means it falls pretty much outside the purview of this class. And that doesn't mean that these are not important. In fact, that in some ways recommends paying even more attention to the the chances that you have events that sort of defy your ability to describe them probability, because just sort of based on institutional weaknesses in planning, but also human psychology, we tend to ignore these events, or we tend to overestimate our ability to predict them. So an example of a black swan event, I would say, is within the California electricity crisis, the market manipulation that occurred partly on the part of Enron, right? So this is something that you can't really plan for, right? You can't incorporate in your loss of load probability model the chance that you have some sort of market actor that acts in an inappropriate or illegal way, right? And so that's sort of the chance of that occurring sort of defies in some way our ability to incorporate it into modeling. And that's a weakness that we have to acknowledge up front when we're talking about modeling the impacts of shocks and failures on systems and the probability of those events occurring. We're always going to have a blind spot, and our blind spot tends to be in areas that we cannot mathematically quantify the chances of them occurring. So it's going to be kind of tough to tell the difference between black swan events and system shocks and failures, at least empirically, right? Like they tend to have the same end result, which are impacts on prices. And the main difference, again, between system shocks and failures and black swan events is that black swan events we can't really describe probabilistically, even though they may have the same mechanistic impacts on the system, right? They may impact, black swan events might equally impact the supply or demand side of things, and act on the same system components as system shocks and failures would. The main difference here is that we can sort of describe probabilistically system shocks and failures, whereas black swan events sort of by definition defy that. And here's another example. So if demand shifts to the right here, while something also causes the supply curve to shift to the left, and there's an error here in the text. It should say while something also causes the supply curve to shift to the left. Again, the price can skyrocket, right? Because the intersection of the supply and demand curve would occur at a much higher point on the y-axis. But so black swan events can cause demand to shift to the right and supply to shift to the left. In some cases, in the exact same way that a system supply or a shock or failure could. Again, the main difference is, we can't probabilistically describe the chances of black swan events occurring. So, and this is the example. Shows the price impacts for wholesale electricity in yellow, natural gas in blue. It's a really nice illustration of how gas prices and electricity prices are correlated here. But this is the polar vortex, right? This is the end result of the polar vortex in early 2014, where you had dramatic increases in the price of both natural gas and electricity because of really, really severe cold weather. And so this is a system shock and corresponding system failures. I mentioned, part of what made this so bad is because we had all these backup coal-fired power plants that couldn't turn on and respond to the increase in electricity demand because of high or really, really severe cold weather. At the same time, you had really high natural gas prices. So not really a black swan event here. I mean, we can sort of describe probabilistically how this would work. The only element of this that was kind of a black swan was the sort of inner workings of natural gas markets, and that caused some specific issues, but a lot of those have been resolved. In fact, we had another really, really cold winter in 2015, and we did not see as severe issues. So how do we model all this stuff? We're going to think about that a little bit in class. We can model this deterministically. When I was talking about the loss of load probability, that was all assuming that we had some sort of deterministic model, an actual representation of a power system, and we'll discuss how to do that. That's mostly what I do in my own research. We'll talk about how to do that in a couple of weeks. The other option is stochastic modeling, right? So we can use time series models, Markov chains, Monte Carlo simulation, and so we're going to do a couple examples in class on Thursday. Alright, that's it. No references, at least not ones that I wrote down, so I will go put this on YouTube. Thanks.